Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 50, we will learn about reinforcement learning. So the different concepts that we will cover will be on reinforcement learning framework, reinforcement learning fundamentals. Then we will learn about the Markov decision process. Then we will look into types of reinforcement learning, temporal difference learning, or otherwise known as TD learning, and then we will demonstrate a model of Q learning in Python, which is one variant of reinforcement learning. So what is reinforcement learning? It is a branch of machine learning where an agent learns to make decisions by interacting with an environment. So that means the agent takes decisions on its own and it tries to maximize a cumulative reward. That means because of these actions he will get rewards, and not the rewards only for that particular step but all the subsequent steps or towards the final goal, and that agent is trying to discover optimal strategies through trial and error to find out which strategy will actually lead to that kind of reward. So reinforcement learning lies between supervised and unsupervised learning to a certain extent, because the agent is exploring to find the right strategy in this particular case, and the agent is not given correct answers, but instead he receives the feedback in form of rewards or penalties based on its action. So that means it will explore different action, it will based on certain actions it will get some reward or it will get some penalties, and accordingly it will take a decision of what to adopt. And again, the reward is not only for the step, the current action, it is also for all the subsequent actions and the changes in the environment that will be resulting in because of those particular action. So the rewards add up till the final goal is reached. So the agent must explore different actions and learn a policy that maximizes cumulative reward over time. So reinforcement learning is grounded in several theoretical foundations. You will see that probability theory becomes very important here for modeling uncertainty and the stochastic environment, because what happens in the environment, certain things could be stochastic, certain things are not deterministic, and then also when transition happens between two different states of the environment, then also stochasticity comes in. Then optimization to learn policies that maximizes cumulative reward, similar to other problems in machine learning that we have learned, where optimization was used to determine the gradient descent and other based on the value of the loss function. But over here it's a little bit different. It's based on we are trying to maximize the cumulative reward that this particular action will generate, and from that we are trying to frame a policy which would be good enough for all the steps, subsequent states that this agent will undertake. So the policy is not one action. Policy is the direction in which that particular agent will act, and it's a set of rules or policies based on which the agent will act for all the different actions. So dynamic programming is required for solving sequential decision problems, because again this is not a single step process unlike other machine learning problems. It's a series of steps, it's a sequential process, and we are able to achieve the goal at the final step. So because there are several steps involved, so it involves sequential decision problems, and to solve that we require dynamic programming, and this is where we use Bellman equations to eventually represent the overall reinforcement learning mathematical equations are actually we use the Bellman equations to express them finally. So also neuroscience is somewhat connected because it is inspired by how humans and animals learn through rewards, like for example dopamine signals are used in case of animals. So you can see that how to design the rewards, that becomes very, very important. That means in a very complex problem, if we are trying to solve using machine learning, for example, how a robot should walk, right? So in that case, the rewards, how you frame the rewards, that itself is becomes very important. So where we apply RL, we apply RL in in large in case of problems which are not so having a definite solution at the end. So usually which involves several steps, and it involves a sequence of steps that that particular the agent has to undertake, or the decision maker has to take. So for example, in case of traffic management, because it involves many many signals, many directions, many steps in the process. So maybe traffic management, smart parking allocation, right? Then energy management in smart grids, autonomous driving, robotics. So this is where primarily we see the use of reinforcement learning. Now, coming to the overall framework of reinforcement learning, first let us talk about the core components. So first there is the agent. The agent is of course the decision maker. That means in case of a self-driving car, it is the car itself, or the the microchip in the car, you can also say that, and an energy or it could be an energy management system. Now, environment is the world in which the agent operates. Sometimes it could be a traffic system, sometimes it could be a city level simulation. So within that agent will execute its action and so on. The state means the current condition of that particular environment. That means what is the situation currently in that particular environment that we are designed, or in which we are actually trying to determine our outcome. So it could be the number of vehicles at an intersection. Then after state comes the action, that is a decision that is made by a particular agent. That is, the decision could be like changing the traffic light timing, maybe that will improve traffic flow. And then comes the reward, because every action there has to be some form of a reward. So it is basically the feedback from the environment, that is, it reducing congestion leads to a high reward. So that means if the changing in the traffic light reduces congestion, that means we should make sure that the agent gets an award for that, right? Award means that this action gets an award for that, right? So the policy means a strategy that maps states to action. That means it will give us a list of states and a list of actions that should be adopted in that particular state if we encounter those possible states. So that is what a policy is. Now over here you can see the learning performance cycle. So that means of course the in the environment the system or the agent operates, and the agent gradually improves understanding from experience. The more he gets trained, more experience he will gather, and he will learn more. And when he learns more, that means he is gathering more knowledge. So the agent has learned, the knowledge is nothing but the policies or rules that the agent is learning. So the more of knowledge he gathers, the more would be the learning, and vice versa, right? And then this is also linked with performance. How well the agent is doing, measured via rewards. So that means if an agent is getting more rewards, that means it is performing well. So this performance and environment is also recursively connected. So this is the learning performance cycle. That means the more knowledge leads to more performance, and eventually it is affecting the environment, right? And the environment also, depending on the environment also, a particular decision is taken. So performance depends on both knowledge as well as the environment. So this and from all this again, from knowledge and environment, again learning or this policy, that means that we are trying to learn, that would come up. So this the next image is a more relevant one, where we are breaking down the entire process. This is actually showing the agent environment interaction. So over here you see that at time t, the agent observes state st. That is that particular environment is in a state of st, and the agent is in part of that particular environment, or it is observing that particular state of the environment. And then the agent takes an action at over here, and the environment responds with a reward rt, or you can say rt plus 1. Why? Because the reward comes in the next step actually. Reward doesn't comes in the first step, right? So and then the next state becomes st plus 1. So that means because of this action, the state changes, as well as the particular agent also gets a reward, and that is also stored. So and then this cycle repeats again and again, right? So that means we are trying to find a general set of policies which will ensure that whatever actions I am taking now, that will lead to try to maximize that particular reward, right? So that means, but the policy that has to be for the entire, not for one step, it is for all steps, right? So this RL interaction loop, you can say it starts with the agent who does an action, it affects the environment gives a reward and also moves to the next state, and then again we go back to the agent and the entire process repeats. And our goal is to maximize the long-term cumulative reward. So now talking about some basic fundamentals before we move into the equations or mathematical formulations. Unlike supervised learning, RL is not a one-step decision, rather a sequence of decisions over time. So this is the first fundamental difference, and each decision affects the future outcome. So that is another thing, that is, it's not that means all steps leads to the final outcome, and the current reward is not optimized, but total future reward is. That means we are not trying to maximize the current reward, that is the step that we are taking now, that may be very good, but we are not trying to do that, because we are trying to do the total reward, total future reward we are trying to maximize, right? So that at the end outcome is good, not the next, this particular state is good, but the final outcome state is particularly good, right? So, so instead of current reward, we go for the entire return, that is the total reward, that is we are taking into consideration the overall return that we are getting. So return GT is the total reward an agent expects to collect from time steps T onwards. From T onwards, this is the total reward that is generated, that is that is what the agent is expecting to collect. So the mathematical formulation of this could be written like GT equal to RT plus 1 plus gamma RT plus 2 plus gamma square RT plus 3 and so on. Now this RT plus 1 is reward in the next step, RT plus 2 is the reward after that, R3 plus 3 is the reward further ahead. So that means we are adding up reward from all steps. But what we are doing is we are also adding a discount factor, which is gamma. So this discount factor is given in such a way so that for the first reward there is no discount, for the second reward it is multiplied by gamma, for the third reward it is multiplied by gamma square, and finally we can keep on increasing this. So this basically means future rewards are progressively reduced in importance. Now why it is so? Because gamma value is between 0 and 1. So there are two reasons for it. One is of course when I put it between 0 and 1, so if I square it obviously or take a cube, the value reduces. So that is one point of it. And the other is if it is close to 1, then the future reward becomes important, that is more closer to 1. If it is more closer to 0, the immediate reward is important. So by choosing the value of gamma, I can decide which reward is more important. The agent learns to choose actions that maximizes return, not just immediate reward. So again and again we are stressing on this because it's a series of steps. So the overall reward has to be looked into. And finally, to summarize all this formula in a general form, we can write GT equal to K equal to 0 to infinity, gamma K into R T plus K plus 1, and this discount factor ensures that the total sum remains finite and learning remains stable. So return is the total discounted sum of future rewards that the agent tries to maximize over time. Now usually to solve this So usually to solve this problem where we are trying to add up rewards for multiple periods, we need to adopt a certain strategy, right? Otherwise we would not be able to do that because we don't know all the steps, right? So reinforcement learning problems, that is why, is typically formulated as a Markov decision process, which provides a mathematical framework for sequential decision making under uncertainty. So that means this MDP, like Markov decision process, allows us to break this sequential process into two steps, that is immediate reward and all future rewards, right? And then we can use this, then we can use dynamic programming to solve this. And MDP, similarly to the normal RL framework, the MDP also consists of a state space S that is given over here, which is a set of all possible states that particular that environment can be in. Then action space A, that is all set of actions available to the agent, what it can do. So it's a set of all actions, because we are using Markov decision process, we have to have a set of all options possible, then only we can calculate what are the outcomes and all. Then transition probability P, that is the probability of moving to the next state S dash given current state S and action taken A. So action taken A is basically given, this is not the case, that is how this is being represented. So this transition probability is represented as P from A to S dash given S and action is A, that is current state S and the action is given is A. So this transition probability is important. That means if sometimes this could be also deterministic. That means we can always say that there are only few states, and the transition is exactly to that state. There is no probability involved. That is, you cannot have different outcomes based on what action you are choosing, right? So sometimes this could be also deterministic as well. But usually real life problems, we will have a transition probability to which step, depending on the action, it will vary. Then there is a reward function, an immediate reward received after transitioning from S to S dash due to action A that you are taking. So that is the reward that we are getting. This is the immediate reward. And then we are also determining a discount factor gamma that determines the importance of future rewards, and that value will be within 0 to 1. Now next, there is, of course, we need to formulate the policy. Our policy defines how the agent will behave, on what are the things that it will do considering certain environments, and that is given by pi A given S, that is probability of taking action A in state S. So that means it basically in a current state, it will have different actions that it can take, and it is given by a probability. An optimum policy or policy that maximizes expected cumulative reward is given as pi star, which is argmax pi expectation maximum value or expectation for the GT, which is nothing but the total the cumulative benefit that we are getting, the cumulative reward that we are getting. So then what happens is, now that we know that okay, we are trying to find the policy which will maximize my cumulative reward, that means expected cumulative reward, not this thing. So we are trying to find the policies which will maximize the expected cumulative reward, right? So that means the next question comes like, then so can we also look into the situation we are in instead of looking into the policies directly? Like, it can be considered VS, that is how good is it to be in state S. That is, we are looking to the value of the state, right? So instead of the policy, I am looking into how good is the state we are in, right? Or otherwise, we can say how good it is to take action A in state S, that is value of the state and action pair. That is, we are trying to find out that which value of the state or which value of the state action pair that will give us a better result, right? Instead of the policy itself, right? So this is known as the state value function, where you can see over here this particular equation. So we are taking the cumulative reward discounted, of course, for different time periods, and it represents, this particular equation represents the expected cumulative discounted reward starting from state S onwards, right? And considering that this policy is pi, right? The policy, the agent follows policy pi for all future steps. So instead of looking into the policies directly, we are looking into the nature of the state or the value of those particular states. Then instead of value of the state, we can also look into the value of SA or the state action pair. That is over here, you can see that Q pi of SA is the expected total discounted reward starting from state S, taking action A, and then following the policy pi, right? So that is what it actually talks about, and then this is otherwise known as the Q function, right? So it represents the expected cumulative reward starting from state S, taking action A, and then following policy pi, which is that is what I just said. So these policy decisions are made using the Q values. So that means we are determining that what is the Q value, and based on that we are finalizing the policy decisions. So we can iterate, right, for which policy we are getting what kind of Q value. So Q value is defined as an expectation over infinite future rewards, and Bellman, so that is it is being defined as an expectation over infinite rewards, right. So you can see over here. So but it is difficult to calculate, right. So that is where the Bellman equation comes in, which gives a practical recursive way to compute it, right. So instead of calculating from 0 to infinity, we break it up into two parts, right. So the Bellman equation is used since this breaks the long-term reward into immediate reward and future value. So this is the two parts in which the overall value is being broken up, and as per the Bellman equation, this is what is given, and so this what is meant is this value of state S under policy pi. That means we are trying to find the expectation or the average, which is average over uncertainty. That is means the average value of a quantity when there is uncertainty or randomness. So that is the expected value. So expectation of reward S dash A plus reward S dash A is immediate reward after taking action A, plus the discounted using the discount factor, which is the indicator of the future rewards, the discounted value of the next state. That is instead of the next reward, we are saying what is the value of the current state and the next state. These two we are taking, so also in a discounted way. So that is what is, we are breaking it up into two parts, that is the future value and the immediate reward. So what reward we are getting now and what would be the value of that particular state in. So the Bellman optimality equation, which is actually where we are trying to find the best possible action, that is we are trying to find the optimal value achieved by choosing the best action, right, which is given by V star S equal to, we are maximizing that for this action A, the expectation of this current reward and the future state of this particular S dash state, the value of that particular state. And then the Bellman equation for Q function, similar to value function and Q function. So here we are using S dash n. This is the one we are going to use finally. That is expectation of this reward from S given A, and then also Y max and the maximum cumulative reward from the next state, right. So that is the next state action pair. So this is also given over here. So this actually this particular algorithm means basically we are breaking the cumulative till infinity of the state action pair cumulative reward into, in this particular form, into immediate reward and the cumulative of the future states, right. So this QSA is the optimal value of state action pair, and this Q star SA is the optimal value of this state action pair. RSA is the immediate reward, gamma is the discount factor, and max of A dash Q star S dash A dash is the best possible value in next state. That is what we are taking, and we are taking the expected value of that of this next particular state. So this is the Bellman equation. This equation leads directly to the Q-learning algorithm. This is what the Q-learning algorithm uses to determine what would be the best possible actions that needs to be undertaken. So while this equation defines the optimal key value, it assumes we already know transition probabilities and expected rewards. So that is the issue. That means what are the rewards and all these things, because we are finding we are looking straight away into the Q value, so it is assumed that we already know this. So this is but actually we don't know them, right. So this has to be discovered by certain strategies. Okay. So how do I do that? So exploration and exploitation are two strategies that allow the agent to discover these values through interaction with the environment. So that means it will do several things and it will find out what result it is getting, and from there it will learn what are the expected rewards and the transition probabilities, right. So these are the two strategies, one is exploration and one is exploitation. Now exploration basically means trying new actions to discover better strategies. That means using a random number, I can start with a strategy, then I can, some way we can transition into other strategies as well. But this basically means that we are exploring randomly, right. Whereas exploitation is using the best known action from previous steps. That means we are choosing the best possible action from steps before. So this actually balance between these two approaches are required for optimal learning. That means I will do some exploration or I will fall back on some known strategies as well. So that is given over here. So choose A, so that this should be some part should be random action and some part should be already known better strategies, the best possible state action pairs strategy that we have to adopt. So there are several ways to do this and there are several exploration methods. The first is the epsilon greedy algorithm, which randomly explores with probability epsilon and otherwise selects the best known action. What it means is, based on the probability value, it determines that will it take a random action or not. Probability value is between 0 and 1. So if that value is within a certain thing, then we are going to choose a random action, and if it is 1 minus epsilon, that is the amount for that value would be the time, that is the number of times we will fall back on the best possible previous action, right. So what proportion will be exploration, what proportion would be the exploitation, that particularly is decided by this epsilon factor. Then there is another method known as softmax, using softmax Boltzmann function. So it chooses action probabilistically where higher value actions are more likely, but all actions can still be selected. And there is also another one called upper confidence bound method, and this selects action by balancing high rewards and uncertainty, favoring less explored options. So there are now coming to the different types of reinforcement learning. Now that we know that using Bellman equation we can actually solve that particular that cumulative reward that we want to estimate, that we can solve, and we are also have to undertake several strategies to find out the values of the learned parameters, right, to understand which policies, which rewards that we are getting by taking different steps. So that is being explored by taking those different steps. Now types of reinforcement learning is actually about how these steps are taken. So the first one is called model free RL, where the agent learns purely from experience without an explicit model of the environment. So we don't create a model of the environment directly. What we do is we learn from our past experiences and all. Of course, there is some exploration, that part is there, but it doesn't means that we have to create our own model environment and so on. So this one example of this is Q learning, which is value based. It learns a Q table of expected rewards for action, and it is the most popular form of reinforcement learning. So that means a Q table is basically a policy table which tells us for this particular actions, these are the expected rewards. So then comes the deep Q networks, DQN. It uses deep learning to approximate Q values for large state spaces, and usually this is used in several high-end problems. It was used by Google DeepMind to beat human beings in Atari computer games. And then there is, of course, another algorithm called SARSA. Then model-based RL is where the agent builds a model of the environment to simulate outcomes before taking action. So that means it doesn't take action; it just create a simulation in which it does several things, and accordingly, it takes action. So in urban planning simulations and robotics, usually this is what is done. That means first you simulate and all, and within that simulation you test if you do something, what will happen, and accordingly you can take measures. So the agent learns a model of the environment, including transition probabilities and reward functions, and uses it to simulate future states for better decision making. So this is how it goes. So it creates, it learns and then applies those learnings into the next steps and so on. So in that way it moves forward. And then, but in case of model free RL, the agent doesn't need to do that. It based on what the experience or based on the action, whatever reward it is getting, based on that it will do. So it is a more straightforward. Then policy based RL is, instead of learning Q values, the agent directly learns a policy that maps states to actions, optimizing it to maximize expected rewards. So here, instead of the Q values, we directly learn the policy itself, right, which will maximize expected rewards. So these are policy gradient methods, proximum policy optimization, and actor critic methods. So these are the different algorithms in this. Now, there is another aspect that we need to learn before we move into explaining one example. So that is temporal difference learning, or TD learning. Now, this TD learning is a method that updates the value functions, that is the state or state action, whichever it is we are adopting, step by step using sampled experience without waiting for the final outcome. So that means we need to keep on adding those values without knowing the final outcome, right? So that means it has to be computed midway. That means during the time the learning process is happening. So it combines Monte Carlo learning from experience and dynamic programming, that is bootstrapping from current estimates. So it will generate new using dynamic programming, it can create those future values and so on. So it estimate those future values and so on. So over here you can see the update rule, which states that the value of state S is updated based on what is expected before and what is actually observed. So in this case, Vs is the current estimated value of state S, Vs dash is the estimated value of the next state S dash, R is the immediate reward received after moving from S to S dash, and then gamma is the discount factor which controls importance of the rewards, and alpha is the learning rate which controls how much we update the particular value. So that means that how much it is updated is based on expected before and what is actually observed. Based on that, we will keep on updating the alpha value, right? So what it does is it compares the predicted value with actual observed reward, and this difference is called temporal difference. So that temporal difference is given like this, right? So this is basically this portion. So that delta is basically the temporal difference, or TD error. So that means it compares predicted values with the actual observed reward from the previous steps, and that is being utilized for learning that how much those actions have resulting in. So new Vs is basically old Vs plus alpha plus into this TD error. So TD to action value methods, so what we can do is, instead of updating the state value, updating action value tells if one is in state S and have taken action A, how good is the particular decision. So that means from TD, that is instead of updating the state value, we can also update the action value as well. And Q learning algorithm is an example of that. So it's a off policy reinforcement learning algorithm. Now why it is called off policy? Because learning uses optimal action, not necessarily the action actually taken, right? So it's a off policy one. SARSA is it's just on policy one. Now the Q learning algorithm update rule comes like this: QS, this state and action, current state and action is resulting from this alpha is the discount factor that we have learned, that is for this learning rate, and this gamma is the value that we are finding the maximum of the future state and action pair, and we are subtracting the current state value to find the difference of this TD TD value, but we are doing it for this state and action pair, right? So this is the Q learning update rule that we actually use in the final algorithms. So the idea is that means we are not having to sum up all the cumulative rewards that we will get, but instead we are checking the steps beforehand and seeing what difference, what kind of what is the temporal, what is the TD error, and accordingly based on that we can also determine that how this updation actually happening. So now coming to an example of reinforcement learning. So this is a very basic example. It probably does justice to the field of reinforcement learning, because reinforcement learning is utilized in so many different things, particularly in robotics and self-driving cars and so on. So it can solve very complicated problems, and where we actually, once the that particular agent to learn the rules properly, right? And it learns based on extensive training, right? So, and then there are different ways that training is also done. So, over here we are simplifying the entire thing just to give a demonstration. So, we are solving sort of a traffic light problem. That means we are trying to decide how a self-driving vehicle must travel through a very simple road system, which has got 4 stages. That means it has a start, it has a road. That means when it after starting it moves to the road state, and then after that it encounters a traffic light state, right? And then eventually it reaches the destination. So, destination when it reaches, there is no policy involved, but in all the other cases it has to undertake a policy or undertake an action, right? And this set of actions, we will try to find out what action leads to what reward, so that we can frame the policies. So, at each state the agent can choose one of 2 actions, stop and go. So, these are the 2 options or actions that are possible, and these are the 4 steps that are there, 4 stages that are there, or 4 states that are there. The agent must learn through repeated trials which action is better in each state. So, we introduce then transition rules. The agent always move forward to the next state, that is start to road, road to traffic light, and to destination. So, it is always a one-way track. So, it is deterministic. So, there is no probability involved. No, it is not stochastic. It is a simple sequential deterministic environment. But in real life it is not like that, right? So, what is the reward rule? What we are framing the reward rule like: at traffic light, if it is action taken is go, the reward is -100. Obviously, that means you shouldn't go in a traffic light. So, that is why we are giving a reward of -100. So, it is an unsafe decision or a red light violation. If stop, reward is equal to +10 if it is a current decision. That means if instead of at the traffic light, instead of go, if the agent is choosing to stop, then that means it is taking an action of stop, it is getting a reward of +10. So, at all the other states, reward given is +1. That means all the other states are what? That means to start, road, and so on. So, because there is a reward to do that, it encourages moving forward in those steps. So, this is just for making it simple. That means we are not bothered with the actual Q values that we will get for state of start and this road and all, because those are not significant. What we need to understand is the car should stop at a red light, right? So, that is why we, for everything else we are ignoring, we are just giving a small positive value, so that the in a simulation or in this particular search for different policies, the movement between those particular states will happen. So, the learning goal is the agent should learn that a traffic light stop is much better, at the traffic light stop is much better than go. So, it should learn by its own. That means we shouldn't tell it, and this is done using Q learning. Now, this we are solving using Q learning over here, and at the end of Q learning, of course, we get a Q table which stores the expected rewards for each state. So, for each state action pair, we see what is the reward, and this is initialized as a 4×2 matrix, 4 states into 2 actions with and it is initialized with 0, and then we see how the values change over once the model gets trained. So, the model starts with standard NumPy as NP, import random, then we are starting with a random seed of 42, so that every time we get the same result, right? We are fixing up the random seed. So, we list the states in the environment, which is start, road, traffic light, destination. We list of possible actions is given as stop and go, and then we create the Q tables. Rows become states, columns becomes action, and then initially the agent knows nothing. So, all Q values are made into 0. So, this is where we are initializing the Q table, right. So, states and action becomes the rows and the columns, and we introduce the learning rate as 0.1. So, this is the alpha value, how strongly new learning updates old value. We already have seen that in the equation. The discount factor is given as 0.9. So, this is the gamma value, importance of all future rewards. So, it is closer to 1. That means future rewards are quite important. And then epsilon equal to 1, which is the exploration rate. So, this is for the greedy function. This is the exploration rate that we are using. That is, initially we are fully exploring. There is no current decision and so on. and the decay rate is 0.01, that is amount by which the epsilon decreases after each episode. That means we are total episode is 100. So after each episode 1 will become 0.9, then 0.09, 0.99 and 0.98 and so on. So eventually it will reach 100. So the more ahead we go, we will choose the better decision, because initially if you start choosing learned decisions, then it will probably have learned rubbish things, right? So better we will not take the initially with the exploration rate is more, and then we reduce it using the decay rate. So for episode in range num underscore episodes, state equal to 0, each episode starts at start and continue until reaching the destination state. So while state is less than equal to 3. So agent is trained for 100 episode. This is the learning experience, starts from state 0 in each episode and loop continues till it reaches 3. So because it's a sequential deterministic state, right? So that is why we are choosing like this. So the Q learning model, the definite state, of course we are initializing the model here, but that means in the overall scheme of things, in this kind of programs, we define the environment, we define the Q learning parameters, we train the agent, then the action selection, that is using epsilon greedy strategy or something, we decide on that. The reward function is determined, the state transition is finalized, then Q learning rule is updated after running this, epsilon decay, display, and then finally we look into finalize the epsilon decay and all that we have done, and we can display the results. So the first what we are doing over here is, that means we are starting, now that we are starting that that movement, that we are training the program. So of course we are starting with the epsilon value with a random seed. That means based on the random number we will start it, and then we can determine how much would be a random choice, and then based on that we can choose this stop equal to 1 and stop equal to 0 and 1 equal to go. Accordingly we are choosing this one, and then so we are choosing things randomly this initially, and then we are based on different actions that we are taking, and that means if state is equal to 2, the action equal to 1, reward becomes -100. So that means we have reached the traffic light and the action taken is 1, which is go, then reward is -100, and if equal to 2 and action equal to 0, reward is 10. So traffic light, basically when we are reaching a traffic light, we are taking a stop decision, then we are getting a reward of 10, else reward is given as 1, right? So in this example, the agent always moves forward in state, because there is a state transition happening. So next state equal to state plus 1. So automatically after each iteration, it will move to the next step, and then this is the Q learning update rule. This we learnt earlier. That is, this is for Q learning. This is how the state action pair value and the alpha, it's a discounted value of reward, and the overall and this is that the difference that we talked about earlier. That is the TD, this part, that is new VS equal to old VS into alpha into the TD error, right? So that is, or you can say over here. So this is what is being happening over here, and we are updating the value, and we are recording for which state we are getting what sort of Q values, right? So that is being stored over here, and then we are moving to the next state. And then epsilon actually help us to decide on that how the epsilon value would be, the decay rate would be, is changing the epsilon rate. And finally, once the agent is trained, that means we can print the trained Q table, and we can print it. This is how it shows. So you can see that this is the trained table for each of this, that is that go and stop, we are getting the values, and so this is step 1, this is step 2, and this is step 3, or state 1, state 2, state 3, and so this is stop and this is go, right? So this is how it is organized. So actually that is over here we have tried to do it in that way. So over here you can see start, road, traffic light, these are the different states, and we have also put the stop and go, and these are the values. So actually we are again printing it in this particular way. And finally we can say that the best learned action in each state. For start, the best learned action is stop. For road, again it is stop. For traffic light, it is stop. Destination also it doesn't have any value. Now we will say that the agent has learned that at traffic light, stop is correct action and go is bad action. But at the same point of time, it has also learned that at start also you should stop, at road also you should stop. That actually doesn't make sense, right? But why this happens is because even though stop has higher Q values in earlier states, the agent still moves forward because state transitions are fixed in this case and independent of actions of this particular simple model. But in real life, it would not be so. So that means because we have framed the model this way, that's why it is moving forward, and even though it is stop, it is still moving forward. And even though stop has higher Q values, because what is happening is earlier state gets positive values because Q learning propagates future rewards backwards, assigning values to states that leads to good outcomes later. So that means because whatever you are taking, you are moving to the next step, and that future reward of stopping is actually getting transferred before. That's why these are also becoming stops as well. So this is how we can do a very simple reinforcement learning program, and the idea is we are just starting with reinforcement learning here. Of course, this is not the course where we can go into depth of it, but what it means is it gives us an opportunity to explore what would be the right set of strategies in a particular situation which we may not even have encountered in the first place, right? So for very complex systems and all, where a lot of outcomes, lot of possibilities can happen, reinforcement learning actually help us to find the right path to move and navigate those sort of situations or environment. So these are some of the references you can study. To conclude, reinforcement learning provides a powerful framework for sequential decision making by enabling agents to learn optimal strategies through interaction with dynamic environments and maximizing cumulative rewards over time. Thank you.